We've walked through the basic rules for doing Lewis structures, but what happens if we have more than 4 bonds involved in our molecules? Then what we need to do is look at the expanded octet rules. And the expanded octet rules only come into play when we're dealing with elements that are in the 3rd row, 4th, 5th, 6th, or 7th, and with elements that have d orbital access. So if we take a look at these compounds, they all fit the category. The central atom, in some cases, is in the 3rd row or lower, and they are in the p block, and they should have at least 4 pairs of electrons surrounding them. So let's take a look at the Lewis structures and see how we would draw their structures. First thing we're going to do, if we remember right, is we're going to count up the number of valence electrons. So if we start with chlorine trifluoride, chlorine has 7 valence electrons. Fluorine has 7 valence electrons, but I've got 3 of them. So I have 28 valence electrons, so that means 14 pairs. Chlorine's going to be in the central spot. I have 3 fluorines surrounding it, so I'll put 3 fluorines in. And I have 14 pairs. So first I'm going to put in the bonding pairs. Now I'm going to put in lone pairs surrounding fluorines. That's 3. 2 more pairs. Where am I going to stick them? In this case, I'm going to stick them on the chlorine because the central atom, in cases like this, is the atom that gets the extra pairs of electrons. So I have a pair of electrons there on chlorine and a pair of electrons there on chlorine. So 2 lone pairs on the central atom. So I have 5 pairs of electrons on the central atom of chlorine. So it gives me a different geometry. If I look at beryllium chloride, beryllium is in the 2nd column, so it has 2 valence electrons. Chlorine's got 7, so we have 14, so we have 16 electrons, so we have 8 pair. Beryllium's in the middle, chlorine on either side, so stick in our bonding pairs first. That takes care of 2 of our 8 pair, and then we're going to do the other 6 pairs. Didn't do it as dots on the chlorine trifluoride, should have. So that's pretty standard, that's the way we've dealt with them before. I can also do ions in Lewis structure format. Iodine tetrachloride, ion. Iodine's in the middle, chlorine's attached. I have 7 valence electrons on each atom, and then I have 1 more extra electron because it's a -1 ion. I have 5 times 7 is 35 plus 1. So I have 36 electrons, means 18 pair. So iodine goes in the middle, chlorines takes care of 4 pairs. 14 pairs to go. Let's put the lone pairs on the chlorines first. I have it drawn now with 16 pairs. Well, I need 2 more pairs. Where do they go again? They have to go on the central atom. That's the iodine. So, as in the first sketch, I'm going to put 2 pairs of electrons on the central atom, iodine. When I do the Lewis structure for ions, I want to put it in brackets, and I want to put the charge of the entire ion outside the brackets. So that's how I draw ion tetrachloride ion. Last ion we can take a look at is nitrate. Nitrogen has 5 valence electrons. Oxygen has 6 valence electrons. So 6 times 3 is 18, plus 5 is 23. It's a negative ion, so that's 24 total, so we have 24 electrons. That means 12 pairs. Nitrogen's in the middle, oxygen surrounding it. So there are 3 of my 12 pairs. Let's put in the lone pairs on oxygen. Right, so I have my 12 pairs drawn, but I have a problem because both oxygen and nitrogen should have an octet surrounding them. The oxygens are fine, the nitrogen is not. So we have to take one of those pairs of electrons that's a lone pair on an oxygen, and we have to move it somehow so nitrogen gets its share of the electrons as well. So when we don't have enough pairs of electrons for each atom to have an octet, what we have to do is move them, and so we combine 1 pair of electrons with a pair that's already there and create a double bond. Does it matter which pair of electrons we take? Not really. So we'll take that pair of electrons from the top oxygen and we will turn that into a second bond between the oxygen and the nitrogen. So here is my Lewis structure. Nitrate ion, again, because it's an ion, I'm going to put it in brackets and I'm going to put the charge outside the brackets. When I'm expanding my octets, the central atom gets the extra pairs of electrons if it should have an octet of electrons and it's in the 3rd row or lower, 4, 5, 6, 7, and it's in group 4A, the group under carbon, or to the right. So it needs to have that octet. It's going to be able to expand. Looking at that nitrate ion now makes us wonder, well, what had happened if we had picked a different pair of electrons from a different oxygen? What would our structure look like? And that leads us to the topic of resonance structures. Resonance structures, what that means is we have more than one valid Lewis structure, and when we have resonance structures, we need to draw all of them. In reality, we really don't have multiple ways that we draw these structures. We don't have double bonds or single bonds in our resonance structures. What we have is a blend of double and single bonds because those electrons actually move. The fact that these electrons in the multiple bonds move is referring to them as delocalized electrons, and they can migrate between the bonds that are involved in those resonance structures. And the resonance model is useful if we want to understand delocalizing and what electrons actually get delocalized. So if we take a look at the nitrate ion, we can draw 3 resonance structures and they look like this. So there is nitrate. First we have the double bond on one oxygen, then the second, then the third. Again, in reality what happens is that double bond is continually moving between nitrogen and the 3 other oxygens. So we don't have one double bond and 2 single bonds. What we have is 3 bonds that are all about 1 1/3 of electron pair. And that's what the delocalization, the resonance, is all about. Our next topic is formal charge. Formal charge, so it's a theory that explains the actual experimental shape that we find with some molecules and with some ions. Sometimes we find that there are Lewis structures that are not resonance structures that we can draw for a particular species. And how do we figure out which one is the best one to draw? So formal charge, like Lewis structures, is another model for representing the geometry of molecules and ions. And the formula that we use to determine formal charge is the formal charge is equal to the valence electrons of an atom, that's VE, minus the number of lone or unbonded electrons, then minus the number of bonds. So let's take a look at an ion and see how we can figure out the formal charge of each of the atoms in it. So we look at sulfate. So we're going to do this formal charge for the sulfur and this formal charge for oxygen. Each of the 4 oxygens in this ion is identical, so we really only have to do 2. So for sulfur, formal charge, the valence electrons for sulfur is 6 minus the number of lone electrons. Well, sulfur being in the middle has no lone electrons on it, so that's 0. And then minus the number of bonds. Has 4 bonds, it's minus 4. Formal charge on sulfur is a 2, positive 2. Oxygen, its formal charge, or its valence electrons, are 6. Each oxygen has 6 lone electrons, and each oxygen has 1 bond. So the formal charge on oxygen is minus 1. The formal charge for molecules, when we're looking at that, and for ions, within the molecule or the ion, the formal charge for each atom should be as close to 0 as possible. So if we look at our sulfate ion, we see the formal charge for sulfur is 2. That's not very close to 0. Formal charge for oxygen is minus 1. That's better. That's closer to 0, but still not 0. The next thing we need to keep in mind is the formal charge, when it's negative, should be on the more electronegative atoms. Oxygen's more electronegative than sulfur. Oxygen has a negative formal charge. Sulfur has a positive formal charge. So that's good. So our first rule hasn't been met. Our second one's okay. The third thing we need to look at is when we add up the formal charge of all the atoms in the species, they should equal the charge of the species. So if I have a neutral molecule, all my formal charges should add up to 0. Here I have a sulfate ion with a minus 2 charge, so if I add up the formal charge for sulfur and the formal charge for all 4 oxygens, I should get minus 2. So I have 2 for sulfur, I have 4 minus 1s for oxygen, so minus 4 plus 2 gives me a minus 2. So this one works. But what we need to do now is see, can we move some of these electrons around so we can make the formal charge of each of the species closer to 0, even the more electronegative atoms. All right, so let's take a look at sulfate. I've moved 2 pairs of electrons on the left and the right oxygen atoms, and they are now double bonds. So let's figure out the formal charge on these atoms now. I have 2 different kinds of oxygens, 2 oxygens with single bonds, 2 oxygens with double bonds. So we're going to put red dots here, so those are their different oxygens. Sulfur, valence is still 6. Number of lone electrons on sulfur, still 0. Number of bonds on sulfur. Well, now I have 6 bonds on sulfur, so the valence minus 0 minus 6 gives me a formal charge of 0 on sulfur. My lone electrons, will do them in black. Again, 6 is my valence minus. I have 6 lone electrons on each of those single bonded oxygens, and I have 1 bond. So those oxygens are minus 1. Now let's look at the oxygens that are double bonded. Again, valence is 6. Number of lone electrons here is 4. Number of bonds is 2. So now I get these oxygens have a formal charge of 0. Now I have 3 of my 5 atoms having a formal charge of 0, the sulfur and the 2 double bonded oxygens. The single bonded oxygens have a formal charge of minus 1. That's not too bad. Again, if I add them all up, 0, minus 1 plus 0 and 0, I get a total of minus 2. So now my conditions are met. Atoms should be as close to 0 as possible. Check. Negative formal charge should be on the more electronegative atoms. Check. Sum of the formal charge for the atom should equal the charge of the species. Check. So when I'm looking at the sulfate ion, it turns out that in reality the sulfate has 2 oxygens that are double bonded, 2 oxygens that are single bonded, rather than all of them being single bonded. And formal charge gives me this information and shows me how to draw it.